Okay, so what do you think will happen to a patient if they receive too little anesthesia?
They'll wake up.
Yeah, that'd be terrible. What about if they get too much? They could die, or it could have a really difficult time waking up. Well, I'm gonna write that. All right, so this formula gives the concentration of anesthesia in a person's bloodstream. And so you can see like it grows and then it starts falling and it kind of levels off. Did anybody notice anything else about this graph? Or wonder something about it? You guys hate those questions, don't you? What did you say? Did you say something? No. Well, there is a maximum, so it does like peak at a little over 2 hours, and then some people in my last class wondered like when does that ever like go to 0? And we'll talk about that in just a second. All right. What is the concentration of anesthesia after half an hour? So you could do one of two things. You could go to 1/2 and just kind of estimate where that is. Or you could actually plug in 1/2 into the function for t. Great. And if you plug it in, you get 2.8%. If you estimated, you might have got 2.5 or 2.9, something in between there. All right, and then number 3 says that the anesthesia is effective once the concentration reaches 5%. How long after administering the drug should the surgeon wait to start the procedure? So here is the 5%. So how long should the surgeon wait? What do y'all think? 1 hour, yeah. How do you know? See, I was in this training yesterday, and they told me that students like to talk. I'm not sure if they've been teaching very long. It's been a long time. It's all right. I know you know, but sometimes the questions are too easy. You just don't want to answer them. So we know because that function is equal to 5 whenever t is equal to 1. Okay. So how long is the drug effective? Between what 2 times is the drug effective? 5% is effective. Between 1 and 6. So how long? 5 hours. All right. It does say to also show algebraically. So we'll do that together. So to show it algebraically, you take the function 35t over t squared plus 6, and you set it equal to 5. Now this is kind of a complicated equation to come back to the first day and start solving. But what you would do is anytime there's something in the denominator you don't want, you just multiply by it. So it would be 5t squared plus 30 equals 35t. And that's a quadratic equation that we can get everything on one side and factor. All right, do you guys notice the common factor on these 5, 35, 30? What divides evenly into all those numbers? Yeah, so we can divide through by 5. Whoops. All right, and then we're going to factor this. So what does it mean about these signs if this last one is a plus? means they're the same. And then you look here to see what they are, and they're both minuses. All right, so we need two numbers that multiply to get 6 and add to get 7. Yes. All right, so that is the same 1 and 6 that we got from the graph, and the difference between those is 5. So there's 5 hours where the surgery could take place. If it's longer, I guess I would have to administer more anesthesia. Okay, and then after many, many hours, what do you anticipate after many, many hours, what do you anticipate will happen to the concentration of anesthesia? After many, many hours, eventually go to 0. Now, someone in my last class really scrolled on his calculator for, I don't know, he was in the thousands, and it never really got to 0. This function never gets to 0. Eventually, I think your calculator will round to 0, but it really never does. But in reality, eventually, the anesthesia does get filtered out of your blood system, and you're back to normal. It takes a long time, though. A long, long time. It does anytime I've had surgery, it takes forever for me to feel normal again. It just hangs around. Okay, and then 6 says, when is the concentration of anesthesia 0? It is. There is one place it is 0. At the beginning, before they administer it. So at t equals 0. Okay, so that type of function right there, that 35t over t squared plus 6, is called a rational function. What is the root word, or what is the root word of the word rational? Ratio. And in math, what does a ratio usually mean? A fraction. Oh, a decimal. A decimal. I don't know what you're doing. Oh, yeah, that's a way to write a ratio with a little colon. Colon, yeah. When I think of ratio, though, good job. When I think of ratio, I think of fraction. So that's what a rational function is. It's a function that's written as a fraction. So let's jot that down. Rational functions have the form y equals n of x over d of x. Where n and d are polynomials. I should have made this fill in the blank. This is a lot of writing today, first day back. Oh, maybe I'll keep you awake. Why do you think I chose n and d to represent these two polynomials? Say it loud and proud. Numerator and denominator. So anytime I talk about n, I'm talking about the numerator. D, we're talking about the denominator. So on a graph, a horizontal asymptote, or any kind of asymptote, is a line that the graph approaches. So a horizontal asymptote is going to be a horizontal line that the graph approaches, something like that. Right, and that anesthesia problem had a horizontal asymptote at y equals 0. Eventually that is going to get down to 0 for the concentration of the anesthesia. All right, so if we're going to find the horizontal asymptotes, compare the degrees of the numerator and denominator. Just do n and d though. Right, so there are three things that could happen when you make these comparisons. One thing that could happen is the degree of the numerator is greater than the denominator. So the degree of n is greater than d. Okay, so I'm going to draw a little line here. We're going to have to put one more thing underneath this in a second. All right, what else could happen when we compare these? All right, the numerator could be less than the denominator. All right, and then what's the last thing that could happen? That could be equal, good. All right, so whenever that numerator is greater, it's a really easy one to do. That's when there is no horizontal asymptote. All right, the numerator is less than the denominator is like the one we just did with the anesthesia. Okay, so the degree of the numerator here was 1, and the degree of the denominator is 2. So numerator is less than the denominator. Would you guys, well, you can't really tell from the graph where it levels off, but we know that after many, many hours, it goes to 0. That's where it levels off. So when that happens, then y equals 0 is the horizontal asymptote. I don't have enough room to write the whole word. And then when their degrees are equal, this is, you need the most space on this one. We have to write the most words. All right, so when they're equal, there is a horizontal asymptote. We're going to draw a big long fraction. All right, so what we do is the leading coefficient of the numerator, which we'll just call n, over the leading coefficient of the denominator, which we'll call d. And that's going to give you the horizontal asymptote. All right, there's one other asymptote we're going to talk about today. There's another one I think I think it's tomorrow we're going to talk about. So these rational functions have so many different characteristics that are going to be really new to you guys, actually, because you don't do this in Algebra 2. But let's do number 1 before we go back and learn about the other type of asymptote today. Okay, so we're doing horizontal asymptote. Horizontal asymptote is all about the degrees. And so what you want to do is just look at the term that has the largest exponent. That's the only one we care about when we're doing horizontal asymptote. Okay, the degree is going to be the exponent. So what do you guys notice about the degrees? They're the same. And when they're the same, the horizontal asymptote is the leading coefficient over the leading coefficient. So just 3/2. And that's it. All right, on B, we need to look at the terms with the biggest exponents. The other ones don't matter. Now they kind of made this harder because they mixed up the order. Okay, so the numerator is obviously greater than the denominator. So what does that mean about a horizontal asymptote? There's not one, so we can say none. Right, and then we had an example on the front where the numerator was less than and it was y equals 0. Okay, whenever there's no horizontal asymptote, sometimes there's something called a slant asymptote. And a slant asymptote is kind of exactly like what it sounds like. So instead of a horizontal line, the graph approaches, it's a slanted line. The graph approaches. That was kind of weird. Okay, so this is a very, very special situation. There's no horizontal asymptote, so the numerator's degree is greater than the denominator's, but more specifically, the numerator is exactly 1 larger than the denominator. Or we'll do D, or you can write denominator. All right, and then to find the slant asymptote, what you're going to do is divide, not dive, divide the numerator by the denominator and ignore the remainder. Now, dividing polynomials, I think, is something we did in our very last test. I feel like I remember you guys doing it. Sometimes you can do long division, sometimes you can do synthetic. Well, you can always do long, but sometimes you can do synthetic. Okay, so on number 2, we're going to find the slant asymptote. There is one because the numerator's degree is exactly 1 more than the denominator. Is this one I could do synthetic division on? Yes. We're dividing by x minus 2. We can do synthetic division. What would I put in the box? 2. Good. We do the opposite. And then we bring over the 1, 3, 2. We drop down the 1. And then from here, it's just multiply and add, multiply and add. Now, if you are one of the few people who like long division, you can do long division. It's fine. It will always work. It's just going to take you a lot more time. It's fine. All right, now we do not care about the remainder. So just like with synthetic division other times, the degree here is going to go down by 1. And so this is going to be y equals, and this would be 1x, or just x, plus 5. So that will always give you the equation of a line, a slanted line. All right, any questions? Some of your faces are scrunchy. We'll talk about it again tomorrow if we need to. Okay. And then this last one is an application problem. So this is pretty common application problem. This one's talking about insects. I've seen these talking about elk population or a deer population or all different kinds of different like things that might be going extinct or they want to build up a population of something. So this one is insects. And they're discovered in the Amazon rainforest. And to protect the species from extinction, entomologists transferred a certain number of insects to a protected area. The population of the new colony 2 days after the transfer is given by this function. Now, the way this is written is not super helpful. We're going to need to go ahead and distribute that 50 in the numerator. Okay. Great. And then A wants us to find the y-intercept. So how do you find the y-intercept of every function in the whole world? You plug something in for the y-intercept. You plug in 0. All right. So when I put in 0, anything that has a t is going to become 0. So we're just left with 50 over 2 or 25. So what do you guys think is 25? If we wanted to interpret this in the context of the problem. Is it insects? Is it ears? What do you think? It's a P. So P represents the population of insects. So 25 insects win. What's the time here? T equals 0, right? Or you could say something like initial amounts of insects. However you want to word it, it's fine. All right, and then B asks us to find P of 15, which is just to take 15 and put it in for T. And you guys can put that in a calculator if you want to, or you can just trust me that you get approximately 184. Not exactly, you do get some decimal, but we're not going to talk about a partial insect. So I'm going to go ahead and tell you, this is going to be 184 insects. But when would there be 184 insects? Yes. All right. And for some reason there's 2 B's. It's fine. We'll just fix it real quick. All right, and then C, we're going to explain what will happen to the insect population after many, many years. So that's similar to this first part where it's after many, many hours. After many, many years or hours or whatever, that's going to be the horizontal asymptote. So if we're looking at the green function of here, remember when we're doing the horizontal asymptote, we're looking at the term with the largest exponent, and we're going to compare the degrees. I don't know if you can see, yeah. So what do you guys notice about the degrees? They're the same. And so we're going to do leading coefficient over leading coefficient. Now, it doesn't have to be the first number you see to be the leading coefficient. It's in front of the one with the largest exponent. All right, so this ends up being 2,500. Now, I used to in biology, my students would know what this is. They must not teach it. It must have, the standards have changed. Have you guys heard of the carrying capacity? Does that sound familiar? No, that's sad. So you have? Okay, some of you have, some of you haven't. So it's like the amount of insects this area can hold before they run out of food, but the population just levels off at 2,500, and that's how much the land can support or whatever. So I would say something like the population levels off at 2,500 insects after many, many years. All right, so what questions do you guys have?